Yes, that is for high speed tunnel, that problem is also there. At least that problem is not there for low speed tunnel, but still your error will become large. Huh. Get Amrita. Amrita is there outside, I think. That particular monochromatic light that was used. I don't know, but Amrita might be. She's waiting outside. She mentioned 630 nanometer. No, it's a monochromatic light, but I exactly don't know which color it was and what is the frequency. Yeah, it's mixed compression intake. No, actually it was say changed with different model. So, it is not a fixed percentage. So, for different model it was different. Actually, we are using some cavities with holes other to control that strength. Yes. Yes. No, actually, see, presenting all the results, that was not the idea. Rather, the idea here was mostly how the experiment was performed, what are the difficulties in that experiment, that is which is consistent with the this class. Okay. As far as results are concerned, I mean, if you are interested, okay, we will make an arrangement and so results for all others. But here the idea was about describing how the experiment was conducted, or so that those who want to conduct such an experiment, they have that. Like we did not even present any say validation of those results and all those things, those we excluded. Here the main idea was how the experiment was conducted or how the experiment should be conducted, what are the difficulties if you are going for an experiment we are likely to face, that was the idea.
There were a lot of bound layers, a lot of imperfections are there because when we do it internal testing. So, in a free flow in a prototype and in internal, what would be the difference in the coefficients we will be getting without like there will be less induced angle of attack in a closed to internal like that and all. So, because of that, in a internal and the free strength means actual flight, what will be the difference in the coefficient?
See, that of course depends from model to model. It is not same for that, but you can expect about even within 10% limit in general. Though in some cases it might be little more or little less, but it is usually in that range. Yes, for a closed section actually that is what get. And so, again we will describe another experimental program. This is flow over or flow past a cavity, a supersonic flow past a cavity, and particularly the cavity flow here was controlled, or rather we are looking for controlling the cavity flow using a V-shaped rear face. In a normal case the cavity is usually all rectangular faces, but here to control it we are trying for a V-shaped rear face. Now, cavities are of course pretty abundant, almost everywhere there is cavity, and in all situations cavity increases drag, cavity gives rise to a drag. I have heard that a human swimmer experiences about 10% drag increase just because of the eye cavities. If the eyes you use a glass and then it becomes this cavity you cover, you gain as much as about 10% of drag, though I am not sure about that number, but it is of that order. So, the cavities are there, and particularly in aircraft, you know, the cavities, the most important of the cavities is weapon bay. Weapon bay, where the missiles are stored. So, the moment the stores are separated, the doors open and there is a cavity. Of course, it is open for a short while, but still that then this landing gear, wheel wells, that is another cavity. In a scramjet engine, that flame holder, that is a cavity, and there are cavities say in cars or any road vehicles or even in any civil engineering structures. Cavities are everywhere, so very prominent. But if we talk about supersonic cavities, then the most important application of supersonic cavity is the weapon bay, because the landing gear, wheel wells are usually at subsonic speed during landing and takeoff, when the wheels are deployed. So, in a supersonic cavity, see the schematic of the flow is like this. A boundary layer grows ahead of the leading face of the cavity, and here the vortices sets. The vortices are set at this leading edge lip, and these set vortices are convected and impacts at the downstream lip here. Once this cavity is impact at the downstream lip, then an acoustic radiation starts because of pressure fluctuation, and this acoustic radiation, it propagates in all direction and also propagates in the upstream. So, this acoustic radiation moves forward like here, and again that acoustic radiation hits here, that causes further disturbance, pressure fluctuation, and again it causes vortex shearing. So, this process, the vortex shearing from the front lip and that impacting on the rear lip, a radiated sound field that comes and again hits at the leading edge, this mechanism, this feedback mechanism continue, and this feedback mechanism creates a self sustained oscillation. There is an oscillation which is sustained by itself, and with that this shear layer deflects up and down, giving rise to an unsteady flow, which often in literature is referred to as mass addition, mass removal. Some of the mass from outside flow is captured by this shear layer, and in next half of the cycle it is again removed, expels. So, this oscillation gives rise to not only a high drag, but also a noise field, and often that noise field is quite intense, having an amplitude of the order of 160 170 dB, and that now noise has some other adverse impacts. So, in supersonic cavity flow, this study of the acoustic field is one of the very important phenomena. So, there are some defining terms for supersonic cavity flows, like a cavity is called deep if its length to depth ratio is less than 1, or it is called shallow if the ratio is more than 1. Usually, a cavity with length to width ratio less than 1 is treated as 2-dimensional flow, otherwise 3-dimensional flow, but there are so much oscillations and so much unsteadiness and turbulence that a cavity flow is rarely ever 2-dimensional in nature, it is usually always in 3-dimensional. Okay. The if the length to depth ratio is more than 13, the cavity is called open cavity. In case of an open cavity, this is the nature of the open cavity, that is the flow separates from here and the shear layer spans the entire cavity and reattaches here, that is called open cavity. When the shear layer from here reattaches only here, that is called open cavity. Sometimes there is the shear layer comes and hits the base of the cavity and there is another from this side. So, that is called a closed cavity. When your length to depth ratio is more than 13, we usually find closed cavity, but if it is less than 8 length to depth ratio, it is usually open cavity. In between we find transitional cavity. Where its occurrently switch, I mean randomly switches between open and closed cavity nature. This we already mentioned, feedback mechanism and this wake mode. Okay, this also we have mentioned where it is found and why it is. These are some cases, the weapon bay, landing gear wheel wells, scramjet engines in the aircraft case. Now, as you mentioned that we did an experimental program on this supersonic open cavity flow. Main focus was of course the noise associated it, and we are also looking if the noise can be suppressed to some extent, can be reduced. Of course, there is no question of any elimination completely, but it can only be reduced. I mean, if the amplitude can be reduced by even 10-15 dB, that is a considerable gain, because that mostly affects with the electronics of the system of the aircraft and also even it has structural effect, because the pressure fluctuation is so large, so intense, that it also has effect on the structures. And so, the experimental measurement are mostly concerned on static pressure measurement and dynamic pressure or unsteady pressure measurement for acoustic computations or acoustic observations. And the experimental program was conducted by a student, Mr. Srinivasan, and he will again discuss about the experiments. But once again the main idea of that is the description of the experimental procedure, how the experiment was conducted. Okay. Results will also be shown, but not many, but how the experiment was conducted, what was the difficulty, how the data was collected, what operations were done on the data, what type of reductions were made. So, that will be the main focus of the description demonstration.
Good afternoon, everyone. So, I will be showing how we have conducted flow field studies over V-shaped rear face cavities. So, talking about, I will be discussing, as professor has already discussed about the introduction about cavities and its complex flow physics, I will be directly moving to static pressure measurements inside cavities. I will be showing how unsteady pressure measurements were obtained and how we are post processing it to get sound pressure level, and some of the oil flow visualization for cavities. So these are the applications of cavities, and which sir has already shown. And the first one is a scramjet combustor. Here we have a cavity which acts like flame holder, which enhances mixing at supersonic speeds. And this is the weapons bay where the weapons are stored, which is mostly found in the 5th generation aircrafts. These are the pressure oscillations, flow physics data. And coming to the model description, we are describing the cavity into 3 surfaces, where this one is the front face, and this one will be the floor, and this one will be the rear face. We have taken length to depth ratio of 5, which means it is an open cavity, where length is of 50 mm, depth with 10 mm and width of 10 mm. All the experiments we have conducted in the supersonic blowdown tunnel, and with the free stream conditions, with total pressure of 3,08,145 Pascal, which gives a Mach number of 2. So these are the nomenclature for various models that we have used. We tried to obtain. With the flat face, here I have described it as CV180. With this V notch, these are the V notch rear face. Flow will be from this direction. This angle we have described it as CV60, CV75, CV90 and CV110. These are the models that were fabricated. If you see, this is a side base plate of supersonic tunnel here, which will be wall mounted. So our model will be of wall mounted. So for different geometries, actually it is of 10 mm width. So we had to change this block rear face. So for that, what we have done is we have made it as 3 blocks. This one will be the base plate, which was manufactured using CNC, completely fabricated using CNC. And for each test, we will be changing this rear face block, maintaining same L by D. That's why this each block will be of different sizes, because we have to maintain the same L by D, but putting the V notch rear face. And if this is the exploded view, and these are the pressure taps. This particular base plate we have used for static pressure measurements only. So these are the port locations. For A is the front face. We have 2 ports, and here we have 8 ports. And on the rear face, which is of more interest, where we have put 6 ports. So here there will be a lot of oscillations. So that's why we have put 6 ports here. And this is the Scannival make ZOC 32 port pressure scanner that we have used. Each will be of individual sensors. So each will have its own sensitivity. So manufacturer, when they supply this pressure scanner, they will give you sensitivity of each semiconductor. So with that, you can calculate your pressure output, because this will be giving you voltage. So you have to convert it with that sensitivity. Of course, there will be some deviation which needs to be calibrated every 6 months or so. So that will be used for correction. And this is a LabVIEW VAE that was used. This is the front panel, and this one will be the block diagram. And coming to the results, whenever we are doing any experiment, actually we cannot start it blindly. So we need to have some reference data. So that's why earlier itself we'll do some computational fluid CFD simulations, and we'll keep that as reference, and we'll try to start our experiments. So unless and when we start at the first time, when we do experiment, there will be a lot of deviation, and because here there will be some leakage at supersonic speeds, there will be some air leakage or something will be there. Either models, every time you have to do some model corrections, or else these ports are of 0.1 mm ports. So there will be some blockage inside that. So you have to keep on testing repeatedly. This particular experiment data that I am showing, it was obtained I think after 25th time. That's why there is very low deviation. And coming to the rear face and front face, actually the cavities have so much unsteadiness that the CFD data that we obtained was of second order only. We used second order accurate solvers, so that's why there is some, but it is close enough to conclude that our data is okay, experiment is okay. These are the static pressure distributions for different V-notch angles. So here if you see, as I am decreasing the angle, the fluctuation this is static, sir. This is not unsteady. I'll come to unsteady next. These are static. That's why usually for unsteady unsteady sensors are different. Actually they have to be wall mounted. I'll show that. These are static pressure sensor.
Which are the locations whatever you are plotting, that locations?
These ones.
Central one or
all three ones. All three. This one is the floor. Floor means this one, the floor part.
this?
Yeah. And this one is front face. Which one will be this one? And this one is the aft wall. Aft wall is rear face, which will be this one. So, giving a consolidated view of static pressure distributions obtained for each V-notch angles, we see that as the angle is reduced, the magnitude of pressure near the rear face, it keeps on increasing. This is only for floor. We have not compared because for V-notch we could not put port pressure port because it is very difficult to put a port there. So that's why we didn't put any port there. And coming to the unsteady pressure measurement, actually unsteadiness, if we are using the same sensor, we cannot gather unsteady because it is we'll lose all the unsteady data. So that's why our sensor should be wall mounted, which will be like this. Which this is of 2.5 mm width with the mesh screen here, which will have some, close to 8 holes. The length will be of 9.5 mm. So this will be inserted here. If you see the front face, we have put one port here. For floor, we have put 2 ports, which will be at the center of the floor and near to the wall, near to the rear face. And for this is the first rear face block. So this is the Cullet company's Cullet. This is the unsteady transducer, and this is the 2.5 cross 9.5. 2.5 diameter. Yeah. And this is the unsteady pressure data. LabVIEW VI, which was used to gather from the hardware. And looking at the sample output for the cavity with the CV180, which is flat face model. Instead, I'm not showing for V rear cavity. If you see this, once we will be getting time versus voltage. So to look at the unsteady data, we need to do FFT and see which amplitude is oscillating at which frequency. So here, if we see these frequencies, mode 1 is around 2500, mode 2 is around 5000, and this is for rear face, because at the rear face only we will be getting lot of unsteadiness. So that's why I'm talking only about rear face. Here there will be not that much oscillations. So mode 3 is of 13,000 frequency. So this amplitude here I'm showing is of voltage. It is not converted to pressure. And if we look for sound pressure in decibel, we use this formula to get which will be 20 log 10 P by P naught dB. The P naught is the reference pressure, which will be 20 micropascal. This is roughly the sound of mosquito flying at 3 meter away. So that will take as reference pressure. So based on that, if you see, P is the current pressure, sir, this pressure, and P naught will be our reference pressure. For air. Generally it is taken as 20. Okay. Yes, that is a practice.
So that's the definition of sound intensity or sound dB, decibel. That is, you find the fluctuating pressure by a standard reference pressure, which actually corresponds to the 20 dB noise, the minimum sound that human ear can capture. That is associated with that reference pressure. 20 micropascal. 20 micropascal, that fluctuation only human ear can capture. Not less than that. So that is taken as the reference.
So looking at then we tried for oil flow visualization also. For getting oil flow, we have to paint our model with black. Actually, when you give any model to any technician, what they do is they do hand painting. So whenever they are painting, they will leave some lump around it, somewhere or the other. So when you visualize that, there will be some unphysical shocks and all. So if you notice that, then you have to remove that paint and you have to refabricate again. So that is common practice. You have to do repeated once. So this was the final result that we got. So we have used a mixture of titanium dioxide, oleic acid, and lubricating oil. Once you spray on that, this is the oil flow path lines obtained in experiment. This one. So for oil flow also we keep CFD data as a reference. Although here, as the cavity was so small, width was so small that whatever data we obtained path lines in experiment, it was not that clear. But here in the side wall you can see the recirculation, which is quite close to what we got in CFD. So we need to keep this also reference before doing experiment. And these are the consolidated results. If you see for CV 180, these are the static pressure distributions, and if we are mostly interested in the unsteady. So here if we see, this is the PSD in Pascal squares. So D describes the rear phase. So here the magnitude with say 5000 Hertz oscillation has very high magnitude. So if we convert this to decibel, here we can see it's reaching up to, mode 2 is reaching up to 160 decibel if we are looking at the sound pressure data. This is only for the rear phase. I am not showing for the other phases. And this is for V notch. While we move to V notches, actually what happened was, in the V notch also, here we could not place any sensor. So what we managed was, we kept a sensor here as C here, close to rear face on the wall. So that's why there is some decrease here. If you see, mode 2 is of only 140 decibel. And as we move, if we see only the V notches, as per our results, as we decreased angle, the oscillations, sound pressure was increasing, which will be up to 150 decibel near the rear face on the floor. If you are looking at the wall, it might be much more larger compared to what we have obtained here, which is of 160 decibel.
This frequency at
That it is of 30,000 samples per second.
Whether it is appropriate or not, how do you
That
has selected this static dynamic pressure
second?
sensor, sir.
sensor. How you have selected?
Yesterday, our Professor Gelberman, this is the point he was. We have to use right
Yeah, right sensors. Yeah.
right sensor, right setting.
Estimated
Otherwise,
Right sensor placed at right location. See, in
so
case of
you should,
cavity, it is more or less well known that the highest sound pressure level you get near the rear corner. Okay. So, but exactly at the corner, putting a
is difficult.
sensor is extremely difficult. Okay. So, usually sensor are put on the floor or on the rear wall, little away from the
My question is how you have selected that transmission, the the range.
the frequency,
Frequency initially they have to
the
know how
expected
much you have to
frequency.
expect some number. Accordingly, you have to select the
even the
No, our
data sampling frequency or
Yeah.
which frequency you are talking?
data frequency.
That much data sampling frequency.
Yes.
That was, I think, your 30,000.
30,000 samples per second, but he is asking about the hardware, sir.
That you have got from CFD data.
CFD data only. Actually, we were expecting for in CFD we take same sampling rate. We will try to do that. From that only we move to experiment. We don't directly move to that.
You can see earlier experiments we have conducted.
Because
They may be
Yeah,
giving
the earlier experiments are also in that range.
transducer, you will get the better.
There are many experiments on in this particular topic, because this is a topic which is widely studied, and there are a lot of information available for this.
Yes.
Those informations are
Please go ahead.
That's it. Actually, we tried, but proper data was not. We couldn't capture anything.
What Mach number you have done this?
2 Mach.
Good afternoon, everybody. I would like to share my experience of designing a supersonic nozzle using method of characteristics during my undergraduate studies. So first of all, this is the motivation why we will use method of characteristics. Then what are the basic components that we need to discuss, that we need to decide before designing the supersonic nozzle. For example, what is the relation of the supersonic compression and the followed by what is meant by Prandtl-Meyer function, and how is it related to the flow inclination, and followed by what is the computational procedure to design the contour of the supersonic nozzle using just pencil and chart paper. So that's the basic design process. Why do we use method of characteristics? Because this is a simple step-by-step. It will give a numerical solution to the exact nonlinear equations, because as you know, the exact system of equations cannot be solved in a simple procedure. It takes a lot of time. Even if you do the numerical procedure in CFD analysis, it takes a lot of time to calculate all those details. So, and moreover, it is a method which gives us reasonably accurate design of a supersonic nozzle. And the reference I am using is that I have used in undergraduate studies, that is Elements of Gas Dynamics, written by Lippmann and Roscoe. It's a classic book that we have followed. So now when you are using method of characteristics, the basic equation of motion that we are considering is that of a two-dimensional non-viscous flow. This is just a simple assumption of a fluid that we will use to calculate the equations in the upcoming slides. But if you use a more complicated flow, the solutions will become a little more complicated. That's it. So this is for two-dimensional equation where you have u1 and u2 are the velocity components in the two directions in the two-dimensional plane. x1 and x2 are the two coordinate directions. So now as we see that this is a partial differential equation, and if we go by the method of finding the characteristics, so we see that it will become a hyperbolic partial differential equation for the condition that u1 square plus u2 square whole divided by a square, where a is the speed of sound, is greater than 1. So that means this is a condition of supersonic flow. So since we are designing a supersonic nozzle, so in this regime, this partial differential equation becomes a hyperbolic equation, and as soon as it becomes that, we know that from the partial differential analysis that a partial hyperbolic PDE has characteristic directions, two characteristic directions in x1 x2 plane, which in the domain of supersonic aerodynamics we call it as Mach line. Now an important feature of this Mach line is the normal derivative of the dependent variables, which are the velocity components. They may be discontinuous, which is not the case in the case of a subsonic flow, because in the subsonic flow all the derivatives have to be continuous, but in a supersonic flow that is not the case, because of which we can attach two different flows on the two sides of a shock. On the one hand side there is supersonic, on the other hand side there is subsonic. So this is one of the reasons for doing that. Now when we derive all those supersonic equations, the main equation that forms the basis for all derivations, that is why I have added this in the slide, is the energy equation, where we have the heat added plus work done on the fluid gives you the increase in energy of the fluid. Now if you assume the flow to be adiabatic flow along with steady and non-viscous nature, the first part will become 0. There is this heat added part will become 0. It only remains is the work done on the fluid that gives us the increase in the energy. Now if we go about the definition of the enthalpy, which is internal energy plus pressure, so that gives us the H plus U square by 2 is equal to H0. That is the enthalpy, constant enthalpy along a streamline. So and for a perfect gas, this H becomes S square by gamma minus 1, where gamma is Cp by Cv. So that is constant along a streamline. Now coming to the supersonic compression, so when we design the tunnel, wind tunnel contour, we have to go by this designing of the walls basically. So here I want to mention one important principle, which is that suppose I want to turn the flow by certain angle theta, so we can do that by giving a direct step of a theta inclination, which will turn the flow obviously, but this will give us an entropy difference in this region, which is proportional to delta theta cube. If you go by the approximation from the weak shock analysis in the mathematical domain, you will find that. Now, instead of doing that, if I divide this single theta step into n number of thetas, which will give us a smooth transition of the flow turning, this gives us something of an isentropic flow, because in that case this delta S, this is change in entropy, is proportional to theta cube, and which you have an n number of thetas and n number of steps in the theta, it is proportional to 1 by n square. So more the number of steps, the lesser will be the change in entropy, and hence this we get to the concept of principle of limited upstream influence, which means that whatever is happening in the downstream is not affecting the development of the flow in the upstream region, and because of which we can build in a step by step manner the wind tunnel in the flow. So this is what I said, that compression by smooth turn is isentropic. So this means that we can start either from the throat or from the test section, it won't matter, because if you go from the throat, it starts from m is equal to 1 to something m is greater than 1. So it's the same thing, because since the flow is isentropic.
From throat it is expanding only.
Yeah,
There is no compression.
there's no compression, it's just the opposite of that. But the process will be the same. So when you design the contour, if we start the flow from that section and it comes to the throat, the flow will remain the same. So it doesn't matter. Now this is the case near the wall. Now if we go away from the wall, we could say that the shock waves or the characteristic lines will merge and become a shock wave, full blown shock wave. So what we will want is that we will want both the walls of the tunnel to be in this region where there is no attachment of the mark lines to form an envelope, so that strong shock is the probability of getting the flow in the strong shock is not there. Now what is the Prandtl-Meyer function? When we approximate a weak shock, we will get a partial differential equation like that. Du by u is proportional to 1 by m square minus 1, where m is the Mach number, and if we integrate it, we will find that where minus theta plus the integration constant is this integral, where this integral is the Prandtl-Meyer function, which is a function of m, Mach number. How we get that? If we do some algebraic analysis, we find that this du by u is a function of dm by m, and hence this whole integral is a function of m. So we get the relation between Prandtl-Meyer function and the flow inclination. So basically we get a relation between Mach number and the flow inclination. So as nu varies from, nu is the Prandtl-Meyer function, as nu varies from 0 to nu max, as Mach number m varies from 1 to infinity. So this is the range of the supersonic flow. Now this relation between nu, m and theta is given in all standard text references as reference tables where we can refer to. So we see that in case of a compression, this integration, this minus theta plus constant is this nu, this will become nu is equal to nu 1 minus mod of theta minus theta 1, whereas in case of an expansion, there is a sign change. So it just becomes an algebraic expression to calculate the contour of a nozzle. It's that simple. Now one thing we need to do is that those equations of motion that we showed is in Cartesian coordinates, but we need to get this algebraic format, the equations in this algebraic format, we need to transfer those equations in the natural coordinate system. So that is S is the streamline direction, n is normal to that. This is the independent variables, and u and theta, where u is the magnitude of the velocity and theta is the direction, flow direction. These are the derived variables, and from that we will again transfer them to that xi eta coordinates, where xi and eta are the characteristics, because as we have seen earlier that in the supersonic regime that equation of motion becomes an hyperbolic partial differential equation. So that is why we will get two directions, xi and eta. So we will transfer our main equation of motion into xi eta coordinates, and while doing so we will have to ensure the compatibility between the transfer, which will give us in a rigorous mathematical analysis, which will give us these two equations, simple algebraic equations, that is nu minus theta is one invariant and nu plus theta is another invariant along the two characteristic lines. So what comes down to is, suppose this is the data curve, we start from here, these are the 2 points, known points A and B, and we want to find the value of the flow quantities at point P. What we need to do is nu 3 is half of nu 1 plus nu 2 plus half of theta 1 minus theta 2 and theta 3 in a similar fashion. So these are basically simple algebraic expressions to calculate the flow quantities. Now one thing is that suppose this data curve is a wall, so in that case our theta will be known and nu will have to find out, because flow inclination will be known along the wall. And if it is an wall boundary, and if it is the boundary, say the inflow boundary or the outflow boundary, there we will know the Mach number. So in that case, if we know the Mach number, that means we know the nu, because nu is the function of m. So nu will be known and theta will have to find out. So in doing so, this nu 1, nu 2, theta 1, theta 2, all these things we can put it in this equation from referencing to the tables that are given in the textbooks. And in this fashion, so this is what I have said. In the boundary wall, this at this point, say H or G or A, theta will be known, and in open sections, say at the inflow, B and C, nu will be given. So based on these informations, we will have to find the values of, in a step-by-step manner, E, F, G and all those values we will keep on finding and drawing the Mach lines. Now we draw these things, but there is one issue, what is where the flow is coming and we do not want the Mach lines to crisscross each other, because in that case we will not be able to find a steady solution for the supersonic nozzle. So what we want is we want to cancel this crisscross of the Mach lines. So what we do is, in a general scenario, we have a simple wave. What we mean by simple wave is the family of waves which have a unidirection, either plus or minus, and wherever there is a crisscrossing, that is called a non-simple zone. Now wave reflection occurs when the boundary alignment is not in sync with the flow turning. So this is what is happening. There is a shock is coming and then it is again reflected. Why? Because this wall is straight here. If the flow turning is in sync with the boundary, then the shock will get cancelled, because in that case anyway the flow has to obey the geometry. So that is why this further reflection is not needed. So this is how we keep on, means we start, suppose we start with this line and then we keep on drawing the contour, so ensuring that the reflection is cancelled, and in this way we will draw the contour. So this is the supersonic nozzle contour that we will finally get. So we start with this sonic line, and this is the initial expansion region. This is some kind of an arbitrary length that we can decide, and followed by this is the reflection zone, because when the Mach lines you start drawing first, obviously there will be a sum. This is the half portion of the contour. These lines are coming from the below. There is this another contour here. These lines are coming from the below, and this is the coming from the above. So if this is a plus Mach wave, this is the minus Mach wave, and they are forming the crisscrossing. So suppose this is an example where the test section area by A star, where star is in the sonic zone, is 1.283, and we want a nu to be of the order of 16, that is m at the test section to be say 1.639. These values you can refer to. So if you see the table on the left hand side, if nu is 16, corresponding to that you will find that mt is of the order of 1.639. So like that. Now when you have these things, suppose you want a theta max of the order of or suppose you want to get the test section only after a single reflection, that is there you have one reflection, and even after that you don't want any reflection. This depends upon you. So if you want that, then you have to have a theta max of the order of nu t divided by 2, that is 16 by 2, that is 8. So this is 8 degree you can achieve in the initial expansion, and then you keep on again converging the contour. So suppose you do that in steps of 2 degrees. So this again depends upon your choice. So 2, 4, 6, 8. So you have 4 Mach lines, and it diverges the flow contour by 8 degrees, and then again you start converging from here again. So that way you at every point you ensure that all those flow conditions and conditions of Mach cancellation are ensured, and then you will get this result. Now suppose this is the situation where I am getting the nozzle just after one reflection. Now suppose you want to get the nozzle after several reflections, and then you get it you want to get it cancelled. So what you do is you divide nu t by 4, so 16 by 4, that is 4 degree. So you have the initial expansion. So that is why I said it is arbitrary, it depends upon the user's choice. So this here the initial expansion will be of the order of 4 degrees instead of 8 degrees. So what will happen, the nozzle will become longer. So instead of 8 degree initial expansion, it will have a 4 degree initial expansion. It will be gradual and it will be longer, and the test section will be far off. So that is how. So these are the changes that users have to incorporate to get to the nozzle geometry. Thank you. Assignment.
Good afternoon. So, in this lecture, we will continue discussion on wind tunnel experiments. I am aware that today you have heard about some experiments that students have performed. So, my lecture will also revolve largely around some of the experimental work that our students have been doing from time to time. Apart from that, we may be discussing more general issues which may be relevant to the topic. So, by now you have a fairly good idea about different types of wind tunnels, how they work, how do they help us conduct different kinds of experiments over different speed ranges, how do you design them, what are the broad principles, and now towards the end of this course we will probably discuss more about certain specific experiments. What are the issues, how are we going to take care of those issues, and what are the different instrumentations which can come in handy for performing such experiments and things like that. So, I start with a very general slide. You are all aware of these points which I have jotted down here, different types of flows, their classification. So, one possible way of classifying them is the speed range which we are looking for in the test section of the tunnel. Could be subsonic, transonic, supersonic, or hypersonic. As far as Reynolds number is concerned, you could have different regimes: laminar, transitional, turbulent, and these regimes may coexist on a given model of interest when you are putting it into the wind tunnel test section. So, it is not that all the model will either see laminar or turbulent flow. It could be a mixed regime. Moreover, you could have steady flows by and large, but certain experiments you might like them to be performed under unsteady conditions because of the relevant issues that you are interested in. In that case, you have to design and build your tunnel in such a manner and also have accompanying instrumentation that you can perform those unsteady experiments. And you should also have proper instrumentation to acquire data at sufficiently high rates so that you can study the flow phenomena of interest. Just as a very general point, I have mentioned about the character of the fluid you are going to use. By and large, in wind tunnels we talk about air being used as a medium. So, air, as you know, under normal conditions is going to behave by and large as a Newtonian fluid, but there could be exceptions. So, if you look at the type of wind tunnel which you are interested in, it will be basically decided based on a few issues like the speed range, which we are talking about the Mach number, through the Mach number here. We are talking about unit Reynolds number. That means if you assume that the characteristic length scale is unity, say 1 meter, then what does the Reynolds number come to? Because your Reynolds number definition in that case is not dependent on a specific characteristic length, which may vary from one flow problem to the other, from one model to the other. So, that is a more generalized way of looking at the problem, that what kind of unit Reynolds number range your model can cater to. Then another very important issue is the quality of the flow that you are planning to have in your tunnel. It can include various factors like what is the, say, free stream turbulence intensity you would like to have, what is the maximum flow angularity that you are allowing, or there could be other issues like what is the extent of uniformity in the mean velocity profile that you are providing in the test section. There could be numerous other issues. So that all put together quantifies the quality of the flow that you are producing in the test section of the wind tunnel. That can affect very much the experiment that you are going to perform in the test section of the tunnel. Also, certain issues like repeatability of results by and large depend on the quality of the flow that you are producing in the test section. So these are extremely crucial issues, and many of these points have been dealt with elaborately by Professor Zilberman in some of the earlier lectures. And again, we need to look at the nature of the working fluid in terms of its thermodynamic state, more relevant for high speed flow experiments. You are concerned about things like stagnation temperature. So we have scientists from DRDL where they do elaborate tests on hypersonic tunnels. So they have to preheat the gas to a very high temperature before they expand it through a nozzle so that they can create hypersonic conditions in the test section. So the gas is certainly not having the same kind of thermodynamic state that say air has when it runs through a subsonic tunnel. So things could be varying widely depending on what kind of situations you are looking at, what kind of experiments you are interested in. And then we have put two stars here, a single and double star here, just to draw your attention to the fact that if you are talking about Mach number, the Mach number is certainly dependent on the kind of test section speed you are talking about, and also the temperature over there, because the acoustic speed will depend on that. And say for example unit Reynolds number, if you are talking about it, it will depend on the test section size that you are planning for. It depends on the cross section, the length, and things like that. So they are all interconnected with each other, and there are more concerns that you have to address. There are important considerations in terms of how energy efficient is the tunnel going to be, because that's going to in a very major way affect your operating costs. So efficiency, I think you have looked at ways of quantifying it, the energy ratio that you have looked at in your wind tunnel design exercise. So that's one way of looking at it. Additionally, you need to look at the kind of model positioning system you are providing. How accurate is it? How versatile is it? How convenient is it to handle that kind of a model positioning system? How much automation have you built into it? And how much human intervention is required from time to time? The model support system. So you can support your system in different ways. You have looked at them. There could be sting mounted systems. You could be actually having other ways of mounting it through multiple struts which support the model and things like that. And also the quality of wind tunnel instrumentation. So that is another major issue, because whatever data you generate through the wind tunnel test, you are ultimately generating it through a system of sensors. Those sensors may be measuring pressure, they may be measuring forces and moments, and other parameters like temperature and so on. So one part is the instrumentation, the other part is how well are you capturing that data. So it's the data acquisition system that has to come into play, and then you have to post-process those results either online or offline, and then finally get those numbers which are so very important for you. And in big tunnels, big setups, the operating costs could be very high. With a single run, you may be spending thousands and lakhs of rupees, and so the data which comes out through that run has to be very carefully utilized, and so you have to take extreme care so that nothing goes wrong while the data gets generated or processed. So there are so many issues that we have to look at, and therefore I thought it could be worth revisiting these points once more. So, we know that when we start using a tunnel, we talk about tunnel calibration. So, airspeed calibration for various speed settings, looking at the velocity variation across the test section, flow angularity measurements, measurement of turbulence level, these are all a part of tunnel calibration. And once you calibrate the tunnel, then only it's useful and kind of ready to be used if you are finding it to be okay. Its qualities are well spelled out and acceptable through the calibration process. Then you look at, say, many things like measurement of pressure, measurement of forces and moments, maybe velocity measurements. So, when you are measuring pressure, again it depends what kind of instrumentation you have deployed. You may be having, say, a completely mechanical system, pitot-static tube, multi-tube gang manometers and things like that. They have been very reliable instruments over the years. They continue to be reliable. But again, each instrumentation may have accompanying disadvantages. So, one of the disadvantages of this, I think you can tell me what it is. Have you handled any? Can you tell me about any limitation of this, say, multi-tube gang manometer? Yes, yeah. The response is poor in the sense that high frequency content cannot be really well captured using that. So, you can actually get mean values pretty well, but if you are interested in the frequency content and things like that, then this is not the equipment you should be looking at. Pressure transducers, yes, the answer must be coming from that end, but then again you have a whole lot of variants and you need to pick and choose the correct one for your application. So, our scientists from different labs, they know very well that you may be choosing to use a conventional, say, transducer like the ESP or Scannival pressure scanners for some applications, but you may be choosing to use Q-Light pressure transducers for other applications. So, it depends on the kind of work you are aiming, what kind of information you are trying to extract and things like that. So, it depends on what kind of frequency ranges these transducers are capable of capturing. So, that is the prime concern. There could be other ways, like we have good work going on in this country also on pressure sensitive paint, PSP as we call them. I forgot to add it here as a point, but that is well known. So, that is another way of measuring pressure, and I am told from literature, at least what I can see, is that that technique is doing extremely well. Force moment measurements, yes, again whole lot of options, mechanical balances, strain gauge based balances. Again, how are you going to deploy them? Are you going to deploy them in the form of internal sting balances or external balances, or there could be still better methods of doing things. So, you can do a bit of reading to find out what more is going on. And of course, the strain gauge based balances, just like the pressure transducer systems here, have to be accompanied by appropriate readout devices, DACs, and of course interface with the computer. And also additionally, you need to calibrate all these devices from time to time. It is not only for the balance, but you need to recalibrate them from time to time, whether it is a pressure transducer or it is a balance. And when you initially purchase it, you may be relying on the initial calibration that has been done by the company which supplied the balance. But over a period of time, we know that the things tend to drift away. So, your results will no longer remain reliable after a period of time. You will find there are aberrations coming up, things which are unexpected are coming up gradually. So, that is time perhaps that you kind of look at recalibration. Velocity measurement, again a very important issue. So, you could have different methods. You may be looking at a single point measurement technique, something like, say, a hot wire anemometer would look at a single point measurement, but say a technique like particle image velocimetry may give you information about a bigger region, not specific to a point. So, again you need to understand your needs and choose what you should be using for that situation, depending on available resources. We have to keep it in mind that we are not going to always have the best of resources for performing experiments. But does that mean that we don't do any kind of experiment at all, or wait for the best things to arrive? The answer is no. We have to make certain trade-offs, maybe some compromises here and there, and still continue to perform some experiments to keep in touch with the actual flow physics. We are much closer to the flow physics. We can connect much better with it once we perform experiments. And we learn through mistakes. So the first few experiments may be having mistakes here and there, but then we gradually learn from our mistakes and try to take adequate measures, and that's a big learning, because learning from mistakes always remains in mind, and also it's going to tell you in future that what all you should avoid doing. So these are very, very important learnings in going through this process of learning how to do good experiments. Of course, for doing experiments we need wind tunnels, and in the wind tunnel, what are we going to put in? We are going to put in some kind of models to test. Models could be of different kinds. They could be scaled down aircraft models, they could be components, they could be other kind of vehicles which are not very much so-called aerospace kind of vehicles, like say cars, like say trains, or even earth fixed structures like say buildings or chimneys. So we are all concerned about their aerodynamic performance in some way or the other. So we first choose which model are you going to put in, because we have a certain problem in mind. So based on that, we have fabricated a model in such a manner that we can position and hold it properly in the test section of a wind tunnel, instrument it properly, and then hope to perform some experiments. So what we see over here is a very well instrumented model. Of course, it's not complete in the sense that, as you can understand very well, that some part of the fuselage of the aircraft over here is missing, but it has been opened up just so that we can appreciate that when we do the instrumentation it could be rather complicated, and we have to plan this layout so very well so that everything finds a proper place inside, and also we get the desired response from all the sensors that we have packed in there, and finally able to extract data which can reflect the flow physics. So there are numerous things which are packed in here. One thing that you can probably figure out is there is some kind of a balance perhaps over here which is fitted in. Many more wires attached to it and other gadgets here, and you also have maybe pressure ports on several parts of the lifting surface. So in that case you will also have pressure tubings running through those wings, and then finally finding their place to a pressure transducer located somewhere. So while you fabricate this wing or say this engine, if you are interested to find out how the pressure looks like on different regions, then you have to plan those components in such a manner that they can be kind of split apart. Tubes could be inserted, again they can be put together, and then those tubes should be running through those surfaces, that means inside, and then finally finding their place through the say the fuselage portion and out of the support system, so that you can take it to the relevant device and make the measurement. The relevant transducer may as well be sitting over here. It may not be at a distance, because that also makes a difference. Okay, your responses may get affected if your sensor is too far away from the source. So you may not like it to be placed very far away from the point where you would like to do the measurement. And therefore, the pressure sensor may be actually located somewhere inside if you are doing a pressure measurement. So instrumentation of the model is a very important issue, and we get a glimpse of that here. Here is a model positioning system. You can understand that there is some kind of a vehicle attached to the model positioning system here, and by actuating it you can change the angle of attack and things like that. So when you are trying to do an experiment where you would like to change the angle of attack, or you may like to change the yaw angle or the roll angle, so your model positioning system should allow you to do all that over the ranges of interest. Again, the model positioning system with all its instrumentation should remain very rigid when the flow moves past it with the model attached. That's another very major requirement. Otherwise, the system may start vibrating, may get even excited to different kinds of frequencies, and those are going to affect your results finally. Yeah, this incidentally is a subsonic tunnel. It is located in Holland, yeah, Netherlands. This is one of the famous tunnels, the DNW group. Yeah. And here you see a sting mounted model with pressure ports on it. You can figure out there are pressure ports placed at different locations. I just put in a small slide over here just to stress the importance of the geometry of a pressure port, which we often tend to kind of forget, that there are major issues linked with the pressure port geometry, and if we don't make it the proper way, the data which is going to come out from that port may be very, very erratic, maybe something very different from what I am expecting. So it may look as like a very innocent orifice, but it has a lot to do with what kind of pressure signal you are going to pick up from it. So this first two lines actually explains to some extent why it is important. So it says that each hole in a wall alters the boundary conditions, producing a curvature of streamlines and hence a pressure change. These effects decrease with the decreasing size of the holes. Usually the streamlines entering the hole raise the pressure, but that's not all. It may not happen that way either. In some cases, the separation of the stream on the leading edge of the hole causes a decrease in pressure. The size of the holes of static pressure must therefore be the smallest possible. Now these are somewhat general in the sense that it gives you certain guidelines in a way, but it may not always be possible for you to follow the guidelines here, and for certain sensors you are actually not going to have an orifice at all over here. You may actually have a sensor inserted here flush with this surface, like the Q-light pressure transducers, which are used very often for unsteady pressure measurements. So in that case, the diaphragm region has to be closest to where you would like to make the pressure measurement, where you need to pick up the signal from. So if you take it far away from the source, you are going to lose information. So here we are not talking about such measurement. This is an orifice based design. So here if you look at the geometry, there are certain characteristic length scales. So you have the diameter of the orifice, say the depth, and then if you are further connecting it with some other tube, then that characteristic dimension, typical length scale of a metallic burr which may be left out after you have drilled it, but you forgot to polish it properly, and other things which are coming from outside sources, like say the Mach number of the flow itself, or the length scale connected with the kind of flow problem you are looking at. So you can figure out that there are a whole lot of dependencies here. We have put it into some kind of a functional form here, where you can see that all these relevant parameters are contributing in some way to give you an assessment of what kind of pressure perturbation will be produced if you have not prepared that small pressure port properly. And mind it that on a practical model you may actually have hundreds of these pressure ports. If it is say a large model which you are testing in a bigger tunnel, the pressure ports are not necessarily few in number, very often the enormous numbers, and you have to take extreme care that each of them are made well. You can see that we have just shown two small pressure ports. If you don't look carefully, you feel as though they are equivalent, but they are actually going to end up giving you very different pressures when you connect the pressure probe to it. One is having a burr on the corner, one is not, but the pressure which will come out of the port finally will be very different, just because you had a layer of bar over here. So, we have to be very careful at every stage. That is the indication. You have heard about these other instrumentations which I am going to talk about in the next few slides, but nevertheless I think it is still worth mentioning that doing wind tunnel experiments, we would have to make measurements of forces and moments. Either we do it with mechanical balances, but these days more often we use strain gauge based balances. So, here we have pictures of a few of them, and very often what we find is that we have to be very careful about what kind of quality control we are maintaining when we are making the balance. So, the balance fabricator, you have to talk to him and you have to figure out what are the major issues. One of the major issues incidentally happens to be, if it's possible, to make it out of one piece of metal. That generally produces the best of balances. There are reasons behind it, we are not getting into it. Of course, the kind of steel you are using or other metal that you are using, that is equally important, and the machining, how smooth the surfaces are where you are mounting those Wheatstone bridge circuits using those strain gauges, how have you laid them properly, and how the forces and moments are going to come onto those sections, how much deflections would be produced, and what would be ultimately the sensitivity of the balance. There are numerous issues which you have to look at. You have to look at the linearity, you have to look at hysteresis, and there could be more in the list. So, it is just not a piece of metal, but very important instrumentation which we need for force and moment measurements in wind tunnel experiments. Pressure scanners, again another very important issue. So, they have been evolving over time, and what we have shown over here is an earlier variant of the Scannival balance, the pressure scanner. So, it so happens that it was mainly because of economic reasons that this kind of a design used to be used earlier, and what is being used today is something like this. So, the issue is that in a pressure scanner of this kind, what we had was large number of ports, say something like 48 ports in a pressure scanner, but only one pressure transducer sitting in the heart of the whole pressure scanner. Whereas, in the modern variants, we have say 48 ports and 48 pressure scanners. So, what made the difference? The piezoresistive transducers which have been used in these pressure scanners have become cheaper over time. That has made a major change in the design. So, earlier what did you do? We used to have a single pressure transducer sitting inside, and from time to time getting engaged with different ports which we have marked in the periphery of this circle, in such a manner that you can scan a number of ports every second, maybe 20 ports every second. How do you do it? Because the length scale over here is not too large, you can make it rotate at a fairly large pace rotationally and scan through so many ports every second. That means over a period of 1 second, if you have scanned 20 ports, then what would happen is that the pressure signal would reach the pressure transducer from one port for a few milliseconds, and then there will be a gap, because then it is not engaged with another port. By the time it rotates to another gap here, you see no signal, and then it moves on to this port, engages, again it sees a signal. So, there would be some pressure, a gap, some other pressure, another gap, and that is the way it used to go on. And then there would have to be very good machining done so that there is no pressure leakage, because you have a rotor and a stator there engaging with each other. So, if you have pressure leakage, what might happen is pressure from one port gets to the pressure transducer through a leakage point which it shouldn't be doing or shouldn't be happening. So, there were enormous issues, but finally the designs which were available from these companies were doing pretty well over so many decades, and we are all familiar, whoever have done measurements with these devices, that they have given us good performance. But nevertheless, the issue was operationally we are better off in the sense that if the pressure transducer broke down, then the balance is lost. It's as good as useless for the time being, because there is only single sensor sitting on inside, so you don't have any redundancy in the system, right? Moreover, there are physical limitations to the number of ports that you scan every second. Beyond a certain limit, there would be increasing errors coming in, and you would not probably manage very high frequency data acquisition. So there could be limitations by virtue of the design itself. So many of those issues have been overcome over time, but economics played a big role. And today, fortunately, we have systems of this kind where we have large number of pressure ports and supporting number of pressure transducers, and they are actually so-called multiplexed. So additionally, we have to keep in mind that the sizes have come down, miniaturization has been possible, and we also have good response of the order of tens of kilohertz, at least 10 kilohertz per channel for these kind of pressure transducers. Another very major part of your instrumentation would be the data acquisition system, where you will actually have a number of functionalities to perform. We have just briefly mentioned them. So you actually, what you are doing in a data acquisition system, which is often in brief mentioned as DAC in the experimental world. The DAC hardware acts as the interface between a computer and signals which are arriving from sensors. Signals could be different kinds of signals: pressure, force, temperature and things like that. But very often when it reaches this unit, it's not really the physical signal we are talking about. We are talking about, say, an electrical signal. That means if you had temperature, you might have used a thermocouple in between. If you had pressure, you might have used a pressure transducer in between. If you had a force, you might have used a strain gauge based balance. You just made sure that they were all converted to some kind of a voltage. And very often those voltages are very weak, very small voltages. Most often we talk about millivolts. And we often say that we excite the sensor with a certain voltage, and when I excite it with so many volts, maybe the full scale could be so many millivolts. That's the kind of interpretation we do. So that means the voltage signals, even full scale, are rather weak. So sometimes we may need to amplify them. Sometimes we may need to do some noise rejection out of the signal that is coming in, and several other functionalities which may have to be met, and that is possible through what is called as a signal conditioning unit. You need to have a very good quality signal conditioning unit in order to really achieve good results at the end of the day. But good signaling good signal conditioning units are usually expensive, and therefore again we shouldn't stop if we don't have enough money to purchase. There are cheaper versions available at a much smaller fraction of the cost of costlier ones, and not that you cannot perform any experiment with them, you can. And the best go would be that we start with such things which may cost much lesser, and still you can do a reasonable job. You have to convert the signal which you have received here through the signal conditioner from, say, an analog to a digital one. These signals which we are talking about till the point where we have handled it in the signal conditioner level are analog signals, but we have to finally get them digital so that the computer can actually handle them finally. So we need to have what is called as analog to digital cards, and then again what they basically do is written here. In practice, analog signals continuously vary over time, and an ADC makes periodic samples of the signal at a predefined rate, and that's how it actually gives you the digital form. And then finally it's going to go to go from the converter to the AD card which you put in the particular slot of your computer, say a PCI or PXI and other slots which are available. so that through that card finally the data gets routed to your software. You need to have the supporting software installed in the computer, which will finally help you to control the whole system. So that's your interface. So finally, a computer with programmable software controls would be used for operating the DAC device. It can help you process, visualize, store measurement data and things like that. So this is a brief introduction, maybe a bit of repetition again on certain important aspects related to internal measurements, including what are the basic considerations, how do we choose a tunnel when we make measurements, how do we use our judgment to choose the proper instrumentation for doing the measurements, and then further how do we balance our available resources with the kind of device we are going to use for the tunnel. So having some kind of a trade-off between the accuracy, the quality of results and the cost of the system again has to be done from point to point. Now with these basics, we are going to move on to look at a few very simple things: pressure measurement, force measurement and flow visualizations in a subsonic wind tunnel. And we will take up some typical problem which is contemporary and which is rather simple for all of us to understand, and we will just see what all can be done in that respect using a low speed wind tunnel. So you can see in this picture, this is an open loop low speed wind tunnel. So you are already very much familiar with the parlance of open and closed loop tunnels. You know the issues, you also know limitations, advantages and things like that. So I don't need to repeat all those. The heart of the tunnel, of course, is the test section, where we are going to mount a model, and in this case we are going to mount some airfoil sections and some finite wing sections. They are very common geometries that we talk about in aerospace engineering, because you see that in all aircraft that are flying around, these sections are used left and right. So they are used as the major lifting devices. So when your aircraft is flying, so until unless you have substantial lifting surface area, you are not going to fly. If you want to control it, you need to have substantial control surface area in order to make the maneuvers. So every time these kind of airfoils or wings are playing some kind of a role. Now when we talk about airfoil, it is to some extent a theoretical concept, in the sense that it is a certain section which is supposed to be two-dimensional. That means out of the plane of the paper, if you have drawn that section, it would actually stretch in the say the z direction. If I consider the plane of the paper as the xy plane, then along the z direction that profile stretches indefinitely, infinitely, without seeing any change. Now you cannot relate that kind of a concept in practical flying configurations, like say an aircraft. You see that yes, there is some kind of a wing section, but it sees an end. The wing is not spreading infinitely across, because then you will not end up having a practical configuration at all. You would not fly at the end of the day. So you have to cut it short in any practical configuration for that matter. So when you cut it short, you are actually producing a finite wing. And of course, an airfoil wing is not a very simple geometry. When we talk about a single airfoil section, we are talking about a much simpler geometry. So on an actual aircraft wing, you may end up seeing different geometries being used across different sections. They may have geometric twists, aerodynamic twists, many more complications. Whereas here we are going to talk about much simpler things. We are going to talk about a single airfoil section or finite wings where the airfoil section is the same across the third direction. So in the test section of the model, we have a small wing mounted. If you can see, it's not all that clear, I don't know. Is it legible to you?
Yes.
Okay, you can see it, okay. And you can make out that there is a round cut like thing and behind that wing, which makes it kind of clear that you can rotate that and maybe use it to remove the wing and things like that. There is also a bigger cut which probably helps you to take the whole thing out, and then perhaps you can get better access into the test section, maybe putting bigger models in, or maybe maintenance activities which need to be done from time to time. So these are important aspects of the wind tunnel test section layout. You have to make it in such a manner that it's useful for you for performing different kinds of experiments. Also, you should have good optical access. You can watch the models, see them while they are operating. You should be able to illuminate the test section. Several other utilities can be thought about from time to time. And the other side, you see that you can perhaps see that circular cut here from the outside portion, and number of wires are coming in from here. They are not electrical wires, by the way, they are actually tubes. They are pressure tubes. So we must be having pressure ports on the surface of that wing, or maybe airfoil. We are not very sure from this view whether it's an airfoil or wing, because if it is an airfoil, it should be stretching from one end of the test section to the other. It should be stretching all the way across the tunnel, leaving no gap at the end of it. That is what makes it an airfoil section. If I cut it short and if I allow air to flow and roll up from the ends, then it's a finite wing. If I stretch the wing too far, very close to the side walls of the tunnel, then the roll up that will occur from the sides will get affected to some extent. So I have to size my model in such a manner so that the boundary effects do not come and affect my results. So today Professor Sinamapatra has explained you how you need to take care about different corrections. So this is one of the issues that you have to look at. When you size your model, you have to look at these considerations so that the boundaries do not affect your results. So if you say that I have sized my finite wing in such a manner that it stretches about, say, 80% of the width of the cross section of the tunnel, then probably you are not going to do a good job in terms of the measurement. Whether it's forces or pressures, it really doesn't matter, because that gap is too small. The wall is certainly going to have an effect on the roll-up. So these are issues that you have to look at. Now coming back to these pressure tubings, you see that large number of tubes are coming, and this is that older version of the Scani valve that I was talking about earlier. I show you this cross section. So that is that single transducer based unit, but mind it has 48 ports, like the way we explained it. So you can actually put in a large number of tubes and then hope to engage from one port to the other, and then finally getting your results. And this pressure scanner is actually getting some voltage from this signal conditioner unit. So that voltage excites the Wheatstone bridge, which is sitting in the heart of that pressure scanner, and that gives us the output voltage from the Wheatstone bridge when it is receiving some pressure. Okay, so you must have set it in the beginning of the experiment and ensured that when it was just sensing the ambient pressure, it was showing you a 0 reading, right? And then when some other pressure comes in, it gets deformed to some extent additionally, generating a certain change in the output voltage from the Wheatstone bridge circuit, and that signal is going to be shown in the readout unit here. And then if you want to amplify it, you can do so. You can do certain other conditionings on the output that you are getting from here. Those utilities are all available here in the signal condition. This further has to be interfaced with the other units we discussed about in the DAC system, so that finally the data reaches the computer if we wish to acquire the data on a computer and process it. Otherwise, we just go by the digital readout that we see over here and try to accomplish the experiment. This is another variant of this, or rather a more modern version of that pressure scanner here. So this is what is called as a DSA unit, and ultimately what you see over here is the data being acquired on the computer. This is a still more newer unit where, you know, I was talking about miniaturization of the pressure scanners, which has happened over time. So, the same scanning valve which was much larger here remained a bit large even in this design, but substantially reduced in size when it came to a design like this. So, some person is working on this unit, and you can see that this is just as big as a biscuit, and it really is very light. So, when you go for the lab visit, you can have a look at this unit, and if you want, you can even take it out and carefully, of course, and see that it does not weigh much. And you can have, say, something like 32 or 48 or even 64 ports available on this, and you can simultaneously acquire data from all those channels at a fairly high rate. You have accompanying hardware here, so it has to be interfaced with all that. Additionally, you have to produce some pressure of the order of say 60-65 psi and provide it to this pressure scanner. There are some specific ports available on the scanner so that you can operate it at a desired mode. So, there are different modes of operation of this scanner. So, you can, in a certain mode you may be calibrating it, in a certain other mode you may be operating it for acquiring data and things like that. Yeah, I will just try to tell you broadly. So, I was this is actually going to get the power supply from the AC line, and going to give the DC power to several subunits here, and then say this has some data cards inside, and this unit is actually a solenoid valve unit, which can be used to provide that control pressure to some ports here on the pressure scanner. So, yeah, it is required because if you provide a certain pressure from these 3 units to those 3 ports which are available on the scanner with a certain logic, that logic is provided along with that scanner unit, then it is going to operate in a certain mode. Okay, it may be a calibration mode, it may be a data acquisition mode. In order, yes, yes. No. This assembly we have done. They would not provide you. So, when they provide you, they will give you the bits and pieces. There may be even small units missing here and there. So, you have to figure out and then configure it properly, and this is done because there are a lot of small gadgets here and there, very expensive and susceptible to damage. So, if you put them together in a nice compact system, probably it is much easier to work with. So, it is a matter of convenience, it is a matter of ease of maintenance and other things, advantages, that we have figured out a system like this and we have put them together. So, but I am not too sure, you may as well be able to buy such a setup from a company. I am not too sure about it. We did not go for that option because we needed our own issues to be addressed. Yeah, compatibility. This is Cannibal, but we also do have ESP scanners. I haven't got. This is Cannibal, incidentally. Yeah.
But the ground one is a Cannibal.
That is also the older one. Yeah. We also work with ESP scanners. This happens to be 3-component internal string balance. We also have 6 components and other variants. So, here for the particular experiment I am going to show you, here we have used this particular balance. So, I thought that it may be relevant. So, this particular one we have purchased. Some of the balances are made in-house, but we are also buying from outside, quite a number. So, I think this has come from Aero Balance in Bangalore. Yeah. So, I think your lab is also having the same person. Yeah, that's right. So, we have had contacts with him for several years. Yeah, and I remember that Dr. Sajir Ahmed had recommended. So, he suggested that we can try it because he had good experience of having used it. So we went ahead and got some units from them, and it's fairly nicely made, and you should have good documentation along with the balance. The matrices which should be available, you know, the cross coupling and all that which you are aware of. So based on that, you know how the balance is expected to perform. Ideally, the coupling should be weak, but it never happens. It never happens. Yeah. So additionally, they have certain fixtures which can help you calibrate the balance from time to time. So there are some utilities which we found was good. They have also put some plastic covering and things like that, so the the strain gauges don't get damaged due to handling problems and things like that. But all said and done, the users have to be extremely careful from time to time, because the biggest challenge is to maintain everything during the regular experimentations and exercises, and until unless we as users don't take extreme care of these equipments, it's very difficult to maintain them well for long periods of time. So care is a very, very necessary issue over here. And another issue is good amount of knowledge and acquaintance with the system, so that at no point of time you are not too sure what is the right practice. That situation should be avoided. So if one is not sure that what is the best way of handling this balance, then should talk to someone who has been handling it from time to time for a fairly long time. So the major concerns would be addressed well, and it goes for any bit of instrumentation, not a balance alone. It applies for any sophisticated instrumentation, costly instrumentation that we are handling. I think we can break for a while before we start the next lecture. Would you like to? Sir, connectors he generally doesn't give, but yeah, these we have our spare units, so yeah, that's right. So we maintain our inventory for all these things. So. So, in this lecture we will continue the discussion on the 3 component sting balance. So, we already talked about several issues here. We talked about the number of channels which are available in a sting balance for measurement. We talked about the interfacing of the balance with the signal conditioning unit. We talked about what other items are available in this box which contains the balance, including certain attachments for calibrating the balance, then connectors which are very relevant, because these are the connectors which we use to connect the balance, and you have matching units at the rear part of the signal conditioner to take those connectors. Yeah, we are having normal force, axial force and pitching moment in this. We are basically looking at the longitudinal characteristics here. Now, coming to the model fixing, I told you that we will be testing both airfoils as well as finite wings. So, when we mount the airfoils, I told you earlier that the airfoils are stretching from one end of the tunnel to the other. That means, from this part of the tunnel to its opposite end, end to end as we say. So, therefore, it is always more convenient to hold the model from the side wall in such a situation, and then you can have say an automatic pitching arrangement over here, so that you can change its angle of attack from time to time. Here the angle of attack is being changed in a static sense. It is not a dynamic change of angle of attack, because we are not looking at the dynamic characteristics of the airfoil. So, I hope you understand the implication here, that the airfoil is a lifting surface. So, there is going to be a difference in pressure distribution between the upper and lower surface of the airfoil. Of course, it depends on the kind of airfoil section you are talking about. If you have a symmetric airfoil section, then at 0 angle of attack, you know that there is no pressure difference between the 2 surfaces, and therefore, it does not generate any lift force. But if you have a cambered airfoil, even at 0 angle of attack, because there is geometric asymmetry, therefore, the flow velocities would be different on the upper and lower surfaces, and consequently, the pressure would also vary, and therefore, you can end up having a lift even at 0 angle of attack. So, it depends on the section, and the point is that if you are fixing it at a certain angle of attack, the pressure difference remains more or less time invariant, until and unless you have pitched it up to a fairly large angle of attack, where the airfoil sees a lot of flow separation, so to say. Flow separation can very often lead to unsteadiness in the flow. I will talk about it in a little more detail later, with some pictures also showing you flow features which will appear quite unsteady. And therefore, if you are say holding the model at a fairly large angle of attack, what will happen is the pressure from one port to the other, if you record it over a period of time, you will see variations coming up. But the same airfoil at a fairly low angle of attack will not show significant time variation. And the other part of it is, as I was telling earlier, that we are not doing the experiment in such a manner that the angle of attack of the airfoil is changing continuously. We are fixing it at an angle of attack, taking the measurements, then moving to the other angle of attack, again letting the flow reach another state of equilibrium, then acquiring the data, not acquiring the data in a transient sense. That is basically the difference between say a static and a dynamic situation. But later in one of my lectures, I will explain a little bit more on the dynamic characteristics, which is equally relevant today because of numerous applications. So, here we are not going to do any dynamic change, and therefore, the model positioning system, which is basically a stepper motor arrangement which you have over here, would fix the airfoil angle of attack when you are doing the measurements, hold it there, not let it slip, and then once you are done with the data acquisition, again index it further to another angle of attack in steps of say 1 degree or 2 degree, which you have decided earlier. It depends on what kind of resolution you are looking at in terms of the data acquisition. You can see several other components here. As you can understand that this is part of the data acquisition system, this is the signal conditioner unit. Additionally, you have another element which you can see over here, that is what is called as a smoke rake. Okay, so this bit of equipment will be used to generate smoke lines, okay, in the flow, and that will help you do some kind of a visualization of the flow. So you will create almost like streamlines of smoke, and how they interact with the airfoil when they move past it, that will be visible. You could have a large number of airfoils and finite wings to test depending on your interest. So here we have put up a few. You can see that some of the models are made out of metal, some are made out of wood. There could be numerous issues in the decision making, but ultimately one thing that matters in a big way is you have to ensure that you have a reasonably smooth surface to deal with. Otherwise, the aerodynamic characteristics could be very different from what you can imagine. So, the surface of the airfoil, you can see a metal model out here. You can see that it is reasonably smooth and polished, but that can also be misleading at times. This does not necessarily mean that it is quite good a model to work with, because if you claim that it is of a certain section, you can see the airfoil section here, the cross sectional view here. So, if you claim that it is so and so section, but if your fabrication method has been erroneous in some sense, then you might not be even having good enough accuracy of the mean profile that you have fabricated. Leave alone the minor undulations on the surface, which is the surface finish aspect. Okay. So, one way you can be very sure about these things is go in for a rather critical check, like say use something like say a coordinate measuring machine maybe, or a similar machine which can measure the coordinates quite accurately and tell you how close or how far are you from the theoretical shape. And then you know that if you are reasonably far, then you are not going to get things right anyway. And then do not blame your data acquisition, do not blame your sensors, because the mistake is right at the root, and mistakes of that order, maybe half a millimeter, maybe a millimeter, can also cost you a lot. Do not underestimate it, more so when you have smaller models. That is the worst part of the story. Why? Because if you have the chord length of the airfoil say 20 centimeters, and there is an error of say a millimeter on an average in the profile, then if you look at that ratio, it is like something like 1:, say what, 200. I mean a very gross kind of a figure that you are talking about. Will you be better off if you are actually going to go for a bigger test section where you can accommodate a geometrically similar model, but where the chord length just doubles, and you still live with a fabrication method where the error max is 1 mm. So, straight away your geometric error comes down by 100%. That is one part of the story. The other part of the story is you have to be careful about surface finish. So, you have very minor ups and downs on the surface. How do they matter? You are tackling a viscous flow. So, you know that flow very close to the surface actually gets stuck in those minor undulations and things like that, tends to form small eddies and things like that, and tends to even drag upper layers and keep them slower. So, if you have a finely finished surface, at least at a macroscopic level, it may be doing a different job from a more rough surface at those scales, and those scales are not to be ignored. because what will finally happen on the surface, whether it's pressure or whether it's velocity distribution within the boundary layer, is going to be massively affected by those small things happening at those scales. So, we shouldn't undermine the smaller part of the story, it could end up playing a bigger role. So, we have to keep good track about both the overall accuracy of the geometry and the surface finish, and as and when possible work with the bigger models. If you have the liberty of using a bigger model, always go for it, because you have certain advantages. Like for example, if you are in an industry where you have to do regular measurements on say aircraft, scale down aircraft models and things like that, what do you look for? You always say that I don't need a very, I don't want, I would not intend to use a very highly scaled down model, because I am sure there would be major scale effects. That is something that we would not like to have. So, that is precisely what we are talking about. If you look at it a little more closely, you see this model has an appendage here. It is some kind of a rod which is fitted to the near to the trailing edge of the model. This is the trailing edge. In this picture, it is this. This is the leading edge, and intuitively you can understand that is used to hold the model in some way. So, you have already seen the 3 component balance. So, you can imagine that if you want to make some force or measurement, say for example, if you want to hold the model with that balance, then you might use an adapter which can be used to connect the model on one end and the balance on the other. But then again, this model is a heavy one because it is made out of metal. So, if you really want to do good things with this, make sure that you make it little lighter. One way of doing that could be take out some metal from inside if you can, without hampering much of the surface finish finally. We have marked certain numbers on these wings, and you can figure out that there are different kinds or series of airfoils that have been used here. Now, these are not very familiar ones. You might be more familiar with things like say NACA airfoils, which are widely used in aerospace and have been studied since long. So, we have a very fantastic and classical book on the different sections, especially NACA sections, which we call as theory of wing sections by Abbott and von Duyenhoff. If you haven't gone through that book, make sure you pick it up from somewhere and go through it. It will be a really good experience. So, there you will mostly see 2 things. Lot of work reported on the NACA airfoils, different series of NACA airfoils. Moreover, they talk about things like Reynolds number dependence on say lift curve characteristic or drag polar and things like that. So, they are concerned about how Reynolds number may be having an effect and things like that. Moreover, they generally talk about Reynolds numbers in the range of millions, and those ranges are actually more relevant for traditional aerospace applications, the full scale aircrafts and things like that. When we talk about them, we talk about huge Reynolds numbers, because 2 things. One is the speeds that we are talking about over there are large in general, apart from certain portions of the mission, and the length scales are also fairly large. So, you know that in the Reynolds number calculation, those are 2 of the important parameters, and if they are large, the Reynolds number in general will become large. The rest of it comes from the viscosity of the medium. So, we assume that we will continue to use air, whether it is a big vehicle or a small, whether it is a wind tunnel or it is an actual flight, it is all air all over. So, that does not play much of a variable role, that is there anyway. So, why are we then talking about other sections here? We are talking because in more contemporary applications, what we find is that it is not always necessary that the NACA airfoils are going to do a great job for you. You may actually have to look for other sections which may be doing better than NACA sections in certain applications. Some of the applications have become more popular in recent times. Like for example, you increasingly talk about unmanned air vehicles, you talk about miniature flying objects like micro air vehicles and things like that, and with fancy configurations also. So, some of the airfoil sections which are in vogue today, you will see that they have been classified as low Reynolds number airfoils. Those airfoils are supposed to give you a superior performance in the low Reynolds number ranges, which the traditional airfoils might not end up doing. You can be reasonably sure that they are not doing it. That is why people had to move in for other sections. So, some of the sections that you are looking at over here, MH or E or S, say for example, E stands for Epler, S stands for Selig. This actually comes from Martin Hepler, if I remember correctly. So, these are sections which are typically more popular in the smaller configurations, where the operating speeds are lower, the characteristic dimensions are smaller, and consequently the Reynolds numbers are of a much lower order. And that is why you are talking about a completely different regime where you have to operate, and therefore, the classical airfoil sections may not be doing the best, and that is how these sections have emerged. So, we have a couple of them over here. A little bit on LabVIEW instrumentation, because we are next going to show you some results on pressure and forces and things like that, and in between we have used a number of VIs. These are very simple for you to devise. If you have not had your hands on LabVIEW yet, please make it a point that you have it shortly. They can also provide you some evaluation versions and things like that. You may not need to buy it immediately, but try your hands and it is a good experience. And the best part of LabVIEW is that it gives you the appearance and the feel of operations going on in front of you, but in a virtual sense. So, you see dials moving, you see indicators moving, but they are all virtual, and but because that appearance helps, you have a feel that you are actually in front of machines and operating them, and you are able to monitor them, regulate them, see how they are doing, and it also gives you a feel that whether everything is going fine or not, whether you need to do some corrective action and things like that. Imagine that if the results were coming in the form of streaming digits on a readout, you would never be able to figure out whether it is right or wrong, or how close it is to the right, so called right or so called wrong. But this could give you a fairly good idea. Intuitively you can understand whether it is going on the right way or not. So, that way it helps. So, some of the students took up a simple project and devised certain VIs, and it gives them the appearance that what are the kind of dials they should look for what kind of VI they are developing. So, it is mentioned here VIs for developed for conducting tunnel calibration. We have talked about calibration earlier, pressure force measurements, model positioning and things like that. So, you can do a whole lot of controls, almost automate the whole experiment through these VIs. Only thing that you have to make sure is that your sensors are doing fine, the hardware, which means the whole tunnel along with the models inserted inside, all the mechanical linkages, everything is doing fine, the electrical connections are fine, and your data is getting streamed properly. So, once you are very sure about this whole setup, there is no reason why you need to worry more. So, you have to run it time and again, foolproof it, and make sure that everything is in place. So, as it happens, you can move towards an increased amount of automation, where you become more free to design the system better and better over time. Just see it performing when it goes on, and it virtually runs on its own. Perhaps apart from some basic functionalities which may not always be automated. For example, starting the tunnel or stopping the tunnel, we would not always prefer it to become automated. There are advantages of having certain aspects available completely in a mechanical form also. Plus, you should always be careful about handling a tunnel carefully, especially when tunnels are of the open loop kind, because by mistake you may move very close to the fan area when you are talking about say a suction type of a low speed tunnel, or you may be standing at the exit of a supersonic tunnel, and even though you may have a second throat, but you never know, things can fly out fantastically fast, and very often things are sharp, and in supersonic tunnels most often models are of metal, made out of metal. If something flies out fairly fast and hits you, could be dangerous. So, when you run a supersonic tunnel, never stand at the outlet of the exit. When you are running an open loop subsonic tunnel, never stand near the fan and things like that. Closed loop tunnels are that way safer, but in general more expensive. So, what we find is, apart from industry, in academia we do not very often have them, whereas the larger risks are actually with students, because they are just getting familiarized. So, I wish that in every lab across the country, in the universities, we had closed facilities, which in my opinion are safer facilities. So, I do not know whether a VI can be developed where you can even track such things, that somebody is getting into a danger zone. So, stop him from doing that. You give an alarm, you may be having a proximity switch somewhere looped into your VI, and that VI signals, and automatically an alarm goes, and you know that there is something going wrong. So, what is the VI going to do for us here? So, the VI is going to do simple things. You have a pressure scanner here, you have a strain gauge balance, you have a stepper motor and drive. That is because you need the model orientation to be changed from time to time, and then you want the VI, to integrate all that along with the LabVIEW hardware. That means basically the DAC which you have over there, and then once you have the VI coordinating all that, you should be able to achieve all this: automated pressure measurement, force and moment measurement, model pitch control, and I told you that there could be several other functionalities. And remember that this is a very simple experiment we are doing. So, the functionalities are pretty small in number. In complex experiments, there could be large number of functionalities, and the experiment may be actually be done in a more complicated way, in the sense that there could be a situation you have a model with 100 ports, but your pressure scanner only has say 36 ports, and now there could be manual error, that when the person who is handling all this, he connects port number 1 to 36 and then acquires the data through the VIs. Next shot he should be connecting 37 to say 72, but by mistake he does something else. So, can a VI figure out that something is going wrong? It should not be a big deal, because it is knowing exactly from where, which all probes. You know that in the new scanner system you have individual transducers. So, it can be tracked, it can be mapped, and therefore, you should be able to figure out that you have done something wrong in the connection. So, one should think that how much the system's capability can be explored and extended. We can exploit it in a big way. So, these are some thinkings that I am doing aloud, which it's not, which are actually doing the job for you. So, this is basically the logic which is working, and you have nice modules which are available within the LabVIEW environment. When you develop the block diagrams, thus just drag and. So, when you have everything in place, you have all the instrumentation ready, your VIs are ready, everything is in place. Now, you go ahead and perform one of the major steps in the whole process, which is called as the wind tunnel calibration. So, here you see that you are looking at several things, it is not a single plot. So, you have say a fan motor RPM versus dynamic pressure, that is one of the plots, all right. So, you need to see that this is actually non-linear, and you need to explain why is it non-linear, that you should be able to explain yourself. I leave it to you to think about. Here you see fan motor RPM versus test section velocity in meters per second, and that looks linear. Why is it linear? That again is a question, and is it supposed to be linear or not? That also you need to argue. So, there are certain things which I am not answering, but I am sure you can answer it very easily. I am leaving it to you to think over. So, there is more. So, now it comes to test section velocity with some normalized distances. That means what we are doing is we are trying to figure out that within the cross sectional area through which the flow is moving, we need to know how much of it is giving us good flow quality. That means, if I am saying that I have such and such free stream speed which I expect at this fan RPM, that how much of the cross section is actually giving me that speed? Is it the whole or is it some amount of it? If it is some amount of it, how little or how much? I need to know exactly. Why do I need to know exactly? Because then I have to size my models in such a manner that all of the models sees the same uniform velocity. If not, then I am going to get very unexpected results. Why? Because part of the model is facing a certain desired velocity, whereas a part of the model is getting much less, which it is not supposed to. Like for example, if you look at this plot, you see the test section velocity, it is of the order of say 14 meters per second, and it is a normalized width. So, the width of the tunnel test section. What do you see very close to the wall? You see that the velocity within a very short distance drops massively, and there could be more points here. If you have a nicely resolved so called boundary layer which is forming on the tunnel wall, then you can have more points where ultimately the value within a very short distance normal to the wall will drop to 0. If not 0, then very close to 0, because 0 will occur right at the wall, and you cannot have a probe sitting right at the wall, because the probe also has a hole and the hole has a thickness. And so, say the mid plane is still some distance away from the wall, that is one. Second point is that the moment you put a probe into the boundary layer so close to the wall, you will be further challenging it, because it is already out of steam there, and the moment you intrude there, it is going to stop anyway, because you are using an intrusive measurement method. So, you have to again be careful whenever you put things into a flow, you are going to disturb the flow, and you need to take care of the disturbances which such equipment can produce. So, all the time, if possible, we try to avoid intrusive methods of measurement, but unfortunately very often we cannot get rid of them. But whenever we use them, we have to use them with care, because all such equipments are sources of perturbation, and how large is the perturbation locally or globally to the flow, that needs to be understood well. So, this is one part of the story. So, we said that we need a good amount of the cross section to be having a uniform flow field, and we see that over a fairly large distance it is more or less uniform. Now, keep one thing in mind, that this is an average data. Okay, you have acquired data for some time and then averaged it. So, it does not mean that all the time when you acquired it, it actually stood at that value specifically. No, it might have fluctuated here and there, slightly here and there, but when you did a time mean of it, you got a reasonably good distribution. Why would it fluctuate to some extent? Because we talked about something called as the turbulent intensity, which is already there in the free stream. If you have some turbulence in the free stream, then there are going to be fluctuations in all three directions. Fluctuations need to be small. That is the intended behavior which we are looking for. Likewise, we look at height and we also see a similar distribution. Then we look across the center line position and we see reasonably good behavior. Once having done all this, we know that the tunnel is reasonably well calibrated and we are satisfied with its behavior, and we also know how much of the area we can occupy to introduce models and make our measurements, and how far can we realize such measurements. Now, let us look at a bit of pressure and force measurements. We have talked about the instrumentation associated with it earlier, and here we are talking about the angle ranges that we test it over. So, it is about -5 degree to T degree that we have varied for the airfoil measurements in steps of 1 degree, and of course, that was controlled precisely by the stepper motor. And remember that when you use the stepper motor, you also have to do some kind of a calibration to make sure that the stepper motor, when it rotates, it actually rotates through 1 degree. Is it 0.99 degree or 1.01 degree? If it does, then that is going to add more uncertainty into your results, going to introduce errors into your results. And if it does, and that is the best you are getting, then you also have to do some kind of a error estimate, some kind of an uncertainty estimate, which are very important issues in experimentation. So, you may have n different sources from where errors can crop in, from where uncertainties can crop in, and there should be a formal way of at least estimating it, so that you know fairly well that what is the expected band in which you are standing and whether it is acceptable or not, whether you need to improve your instrumentation, your experiment, the designing of the experiment has to be improved, so that you can get more acceptable results. Now, coming back to the sections that we are interested in, I have already mentioned some of the sections are little more recently popular sections, and they are typically being used in different kinds of UAV, MAV configurations. You can see one UAV flying here, and we have shown Reynolds numbers which are far too small compared to what we talk about in conventional aerospace applications. They are just of the order of 0.1 million. Maybe even if you increase it a little bit more, it will fall well short of a million. And
passenger aircraft, what is the Reynolds number?
It goes to the range of 10 raised 6, 7 order. So, you are, yeah. So, you are at least 2 orders off from there. So, the aerodynamic behavior can change significantly. This is a small slide which talks about what are the effects of such reduction in Reynolds number. Since we are now going to operate in the low Reynolds number regime, we will have effects with which we have to live, and we see that in low Reynolds number regimes, quite a bit of the flow as it develops on the airfoil could remain laminar, and laminar flow is not as robust as turbulent flow. This you have learnt in your fluid mechanics courses. And when does it actually matter? It matters when you are trying to, say, pitch up the lifting section to a moderate angle of attack at angles where the sections are not expected to stall and things like that. You may suddenly see such things happening in these Reynolds number regimes, because the boundary layer is still laminar and it is very much susceptible to very moderate adverse pressure gradients. It can actually separate off, which is a very dangerous phenomenon, because if the flow separates, you know that the flow behaves very adversely beyond that. There is enormous loss of lift, there is increase in drag, and therefore, the aerodynamic efficiency of the lifting surface massively gets affected. That is the L by D ratio we are talking about. L drops, D increases, and therefore, L by D, the ratio, is going to suffer very adversely, and therefore, the aerodynamic efficiency will be lost. So, if you are going to design configurations which are to operate at low Reynolds numbers, then you have to be aware of these issues, and you have to design it in such a manner that such problems are averted or tackled in real time in some manner. One thing that you always should do is choose the section, the airfoil section, which works better in the lower Reynolds number regimes to begin with, and then put add-on measures which can perhaps help to further improve the performance. It may not be just the lifting surface alone, it may be the entire configuration which you may have to redesign, rethink. So, one of the issues here is the formation of the so called laminar separation bubble, and we will show one slide just to give you some picture of what actually happens. These kind of things are rarely seen in the high Reynolds number regimes, which we are talking about for the bigger aircrafts and things like that, but very often happens in the low Reynolds number regimes, we see that in the initial part of the flow to quite some distance the flow is still laminar, and when just minor adverse pressure gradient effects start getting felt, on that verge the boundary layer very easily tends to get separated, and therefore the streamlines tend to lift off from the surface and things like that, and there is usually a transition which occurs in between, and that helps the flow to reattach back again under certain conditions. Here the flow has already gone turbulent, and because it has gone turbulent, it is able to sustain the further adverse pressure gradient which occurs over here and separates finally much later. But what has happened in between is that a pocket of separation has formed, and that is looking like a bubble. It is a closed bubble which is sitting out there on the surface of the lifting surface, and it seems to be stable, but the reality is that very often these bubbles also tend to remain tend to show some instabilities, and with a slight change in angle of attack it may in fact burst and finally become completely separated flow, which will never tend to reattach again. So, that can lead to again massive degradation of the aerodynamic performance. So, one of the major research challenges in association with these kind of flow regimes is that how to tackle the laminar separation bubble, if possible eliminate it or keep it stably attached and things like that, so that the aerodynamic performance does not degrade. And the whole physics is actually outlined over here, where you must have seen what is going on, that the flow, as long as it is in the favorable pressure gradient, the boundary layer seems to remain quite robust, quite energetic. Moment it goes into the adverse pressure gradient, there is crisis, and then there could be flow separation and recirculation further. Now, typical signatures of this laminar separation bubbles may be found when you do the pressure measurement on the airfoil. So, all the time we were talking about measuring pressure, measuring forces. So, this is the first plot we are seeing where pressure has been measured on those sections. One of the sections we are showing the behavior for 3 different Reynolds numbers and at 2 different angles of attack, and you see that this part of the airfoil is the upper surface where the pressure coefficient is negative, it is below the free stream pressure. Okay. So, there when you have a laminar separation bubble, normally you will have a big spike and then a plateau extending up to the bubble region. Where the bubble closes, there is a sharp fall like this. This is a typical signature of the LSB. So, what you see that at alpha equal to 6 degree, we do not see any signature of it, but it has come up at 10 degrees. All right. But if it was a fully turbulent flow at 10 degrees, we might not have seen signatures of this kind. I am sure for the conventional Naka airfoils and things like that, you might not have seen signatures of this kind. They are rather very typical of the low Reynolds number regimes. So, this is the typical pressure plateau that we are talking about, which is usually seen for the laminar separation bubble reattachment regions. Now, if we look at the lift coefficient, how it behaves with angle of attack for these airfoils, we will see that we have tried comparing with some results also which are published in literature, and even after repeating the experiment several times, we could not match the results all the time so closely with what was available in the literature. And we were pretty much sure about the repeatability of our experiments. So, we started looking into the different sources of uncertainties and errors which could have crept in, and then we looked at several different issues, and I have just pointed out some of the issues which could be relevant. And when we do experiments, we have to go through this exercise time and again until and unless we get very satisfactory answers that we have done a good job and we have not left any stone unturned to improve the experiment and take it to the best. So, the first point that I have written over here is method of measurement and calculation of the coefficients, whether it is pressure or it is forces. You have to be very sure that what you are doing and what the experiment is being reported, the measurement and the calculation methods are comparable or identical. What does it mean? It means this, that here how did I generate the lift coefficient data? The technique was, we measured pressure, we integrated pressure, and we generated data. Why we did not use the sting balance? Because it was a end to end model. When we tried holding it with the sting, it was exceeding the sting's range. So, we preferred to drop that method altogether, and we preferred to side mount it and just do pressure measurement, and thought that we will integrate the pressure and see that how close can we go to experiments which are reported in literature. Mind it that the experiment which is reported in literature is not done by that method. They have done direct force measurements. They used an external balance, they have also used side mounting, but they have an external balance outside, it is not sting mounted, and they could get the forces directly. What difference does it make? There is a major difference, in the sense that in some of your first classes you have learned that on say an airfoil section there are two things which work at a point. It is the pressure and it is also the shear stress, the skin friction. Both of them are important. And if you are just integrating pressure and hoping to get your data, you are wrong, because you are neglecting the skin friction altogether. You are missing out somewhere. So, that might be one of the reasons why we are not able to match it here. So, later we have changed our way and we got much better results, but I am not showing it here because this is more relevant, that why it did not match. There could be other things, there could be boundary corrections where what they have done and what we have done are not matching. Generally it gets close, but the point is that if I am not getting the best of matches, I should make sure that my methodology is also comparable, so that I do not have any place to doubt. You may be absolutely right that that component which I have not captured ultimately, because I did not do the force measurements directly, may be a small part, but how do I know that how small it is and how much it would have offset the results. So, it is anyway a source of error, and that is what we realized down the line. So, I also do not know that what is the exact quantification, but I understand that this is a loophole in the method. Yeah.
Normal force is matching?
Yeah, normal force is not too far, you are right. We are missing out on the axial force. Yeah, you are right, you are absolutely right. Yes, that is where the problem is. Yes, we expect that. And yeah, the blockage, you have discussed it in the morning, blockage, horizontal buoyancy, there could be so many different issues. The tunnels are different, so we will have different turbulence intensities which can make a difference, the flow qualities could be different. It is very difficult to quantify all that. There could also be other sources I have already discussed, model geometric imperfections, surface finish issues, positioning inaccuracy. There could be many issues which we have to look at. We have to look at repeatability, uncertainty, quantification. So, it is a very, very elaborate procedure. It may seem simple, a simple airfoil mounted in the low speed wind tunnel test section seems a trivial problem, but no, it is not a trivial problem. Again, sufficient number of samples and the data acquisition rates, this could matter. When you are looking at means, I do not know how much it matters, not always, but when you are planning to extract frequency information, yes, it certainly matters. You are taking everything to the frequency plane, you are doing a FFT of the data. So, in order to get your spectrum right, the dominating frequencies, if there are any, right, you need to have sufficiently high scan rates and acquisition rates, and that will have a significant impact. And what we saw was that in the linear part, as we call it, though you can find that low Reynolds number behavior is very peculiar, even in the lower angles of attack, where we generally are familiar with very linear behavior, it does not always happen here. That is our direct experience. We have done these measurements many times, many times. Every time it comes back with the same nonlinearity, and it is quite strange. Yes, if you look deeper into the flow, you get better answers, but then you have to really look into the flow. We are just looking at integrated effects, whether it is force measurements or pressure and things like that. And in the stall, post stall regions, of course, we had to use much bigger sample sizes, so that we get reasonably good data. So, these are obvious things though. Now, if you look into the finite wings, that means you use the same cross section, but make the wings finite, right. So, you allow the tip roll up, as we say. So, when you put the model into the test section, the flow can roll up from the end here and there, and then the aerodynamics changes very drastically. Some of you might have seen how flow rolls up around a delta wing, for example. If you have not seen, then look up some material in the web, and you will find fantastic visualizations which can give you a good idea that from the leading edge of a delta wing, how flow rolls up, generating very strong vortices, and that is what keeps the wing going even at very high angles of attack. And this is a very regular phenomenon, which is very carefully and intelligently used by our fighter aircrafts. And it is not a simple delta that they are often using, they are using all kinds of tricks to play around with the flow there. And you will also find that somewhere it is sharp, somewhere it is a little blunted, you may have strakes, what not. So, there is a lot of playing around with the flow at the high angle of attack, which is done in those configurations on a regular basis. So, when you play on finite wings, even here when you are planning to do it for, say, a much low speed application like a micro air vehicle, similar things are going to be encountered. Of course, because of the operating speeds, you would not talk about compressibility effects. Say on a high speed aircraft, you will additionally have effects of shocks and things like that. That will never come up on this, but you can see through some oil flows that how much impact that roll up can have. If you have the picture at 3° angle of attack, the black patches which are there on the sides, they are rather weak. Those black patches are being created because of the roll up. They become much wider and reach much more inboard, almost eating away the entire span of the wing when it goes to 15 degrees. And surprisingly, this is what will have a major impact on the aerodynamic characteristic. When you look at the lift curve, it will look different. Two things you have to watch out for is at what range of angles is it stalling. The other part is the slope of the lift curve. So, that because of this, it is going to sustain up to much higher angles of attack, which delta wings also do. And what happens to the slope, that part, if you are aware, it is good. If not, try to explore what happens to that, whether it becomes steeper than what you see on the airfoil section or it gets shallower, and if so, then why. So, we have shown a small MAV model that was built several years back in one of our labs, our aero modeling labs. So, this is a typical configuration where we talk about such small aspect ratio wings. And then when you look at force and moment measurements here, sorry, yeah, sure. Yeah.
Balance is also subjected to the flow, no sir. So it will have some load on that. Whether the balance measures only the load due to airfoil or also measure the load on the balance.
Yeah, I mean, of course, you have to make sure that finally you are able to get the aerodynamic forces only extracted from there.
How do we subtract?
Yeah, the dead weight part, I mean before you start the test, you have to do the setting so that you can actually eliminate the dead weight part. Yes, that is a little issue that is always there, certainly. Yeah, these are the force and moment measurements, as you can see. So, one thing that I have to again repeat over here is that earlier what you saw for the airfoils, there the lift was obtained by integrating pressure, if you remember, because of the kind of arrangement we had, but here we are going to measure it directly. So, it is both pressure and shear forces which are actually playing a role here. And you know, as far as the normal force is concerned, you know, it may not have so much of significant effect as Dr. Satyanarayana has rightly pointed out, but yes, we see more impact on the axial part. And here the stall angle is higher, of the order of say 20 degrees. If you remember earlier, this was stalling at much lower angles, maybe 7-8 degrees, very small, but you have to look at what the lift curve slope is like. That I leave it to you to think about. They were repeated at different Reynolds numbers, and you can see marginal improvement coming up as the Reynolds number becomes slightly larger, which is again expected. If you increase it several orders, then you are going to see characteristics which you know you usually see for the higher Reynolds number regimes. And if you look at the von Duysenhoff's book, probably will it will give you more inputs in that direction.
You had other
yeah, that is right. We could strike better performance, yes, with the finite, yeah.
Previous slide, sir. The alpha 15 degrees, the lift is decreasing because of that blanketing. The lift gets reduced.
No, actually, what is happening is that I have a stable vortex here, you know, somewhat similar to what you see in the delta wings. So, until unless that disintegrates, I am still going to have fairly good performance. Once that disintegrates, it is going to be difficult, like what you see in the vortex breakdown, for example, on delta wings. So, once such phenomena sets in, we will also see a degradation in the performance here as well. So, I have not included pictures at say maybe 20 plus, which could have shown some more details on that. This is still not separated. Yeah, this is the drag variation again over that same range of angles of attack, and a bit of flow visualization which you can look at. So, yeah.
This right side, that is a higher angle of attack.
This one? Oh, yeah. That's right. Yeah. So, this is I do not know, maybe few degrees, whereas this looks closer to maybe 15. So, I do not know exactly.
Lines are smoke lines.
Yeah, but these are not our experiments. I have just taken it from some place. I forgot to acknowledge this is from a NASA site, but this is, I guess this is also from some university site. I am sorry, I forgot to acknowledge it here. Is that all, or yeah, okay. So, we tried to do some smoke flows, and you know, on the airfoil sections you can see that, you know, some slight separation setting in here, the bubbles, I mean here you know, you do not see the bubbles very clearly. I guess I should have given you a bigger picture. One of the cases we could get the bubble more prominently, but here the separation seems to increase as the angle of attack increases almost monotonously. The same things we try to repeat on the finite wings, where you can figure out that you know, the flow rolls up from the tips, which you do not see in the case of the airfoil because it is end to end. So, we have done that at mid span, whereas here we purposely did some experiments where we could get the smoke lines closer to the outboard section, so that we can pick up the roll up. That was done purposely. Yeah. So, we repeated it on certain other sections also. You can see it more clearly here perhaps. Yeah.
In this part, to get the color, what you have to
Well, this is not blue smoke, by the way. It is just the lighting which gives you.
I mean, background is black, like oil flow, what we are
Yes,
doing,
yes,
same thing.
yes. Matte finish, shouldn't be a shining surface, right? And of course, illumination is on from top. Try to get your optical access as good as you can, right? And another thing that you have to be careful about is that these are very simple principles, though it works. I mean, where you are injecting the smoke from that rake I showed you, it is a very simple device. I mean, everybody knows how to do it. But one thing what we saw was that try to maintain as less difference as possible between the injection velocity and the free stream velocity, because it is a known fact that you will have instabilities at the interface otherwise coming up very quickly, and it will disintegrate the stream very easily.
Both velocities should be same.
As close as possible. Otherwise, your KH instability kind of phenomena are very easily going to set in. There will be a lot of shear acting, and that will break up that streak, because that rake is not very close. I mean, it takes some distance to reach. So, you have to make sure that it remains undisintegrated, stable enough, so that it can cross all this length and show you the features. Otherwise, if it gets mixed up altogether, it is rather difficult to get the features well. So, these are refinements which one can try at a very small laboratory level. Our students have only tried it by hit and trial, that why all this happens, and it is just basic physics which tells that why it works well when you have lesser difference between the two, and we saw it happen. Yeah, but they did a lot on the lighting part and things like that, which brought clarity, certainly, yes. Some more of it, and this is all rudimentary stuff. I mean, if you just put a few tufts on the surface, you have to put them in sections like this, and it gives you some feeling of the flow, though this is not good for a laminar flow. I have told you already that laminar flow is a very vulnerable kind of a flow. So, if you are putting anything of this kind, it is actually tripping the flow, and in fact, perhaps making it turbulent much earlier. So, the behavior would change altogether. So, if you say that if I am putting tufts and that gives me a reasonably good feel of what is going to happen on the airfoil section, or rather the finite wing section, it is not necessarily true that the same things will happen when they are not there, because they are a source of perturbation, and that perturbation may actually change the nature of the flow at those low Reynolds numbers. So, it should not end up become a self defeating effort, but here it has been purposely done to show you that here is a method which can be used to get reasonable information about the flow. Should not be dumped just like that, may be considered carefully. We have used both, but later on we preferred to use our own ones, and no, you have to take some care. You have to take some care and threads, but both the maintenance, the gaps, how you stick them, and from time to time maintain them, that makes a lot of difference. Again, another very simple method, but what makes it difficult at low speeds is much lower shear acting on the wall of the surface. This same technique at high speeds could sometimes be easier to get. We have found that you mount a model into the wind tunnel, you wait for 15 minutes, 20 minutes, half an hour, still things do not stabilize. They keep moving slightly, but on the other hand, it is getting dried up. So, what do? You have to strike a balance. Of course, again you have to play with humidity which is there on that particular day, and here at Kharagpur we can have whole lot of variation. And then you have the oleic acid, and you have titanium dioxide, the humidity in the atmosphere, everything put together, you apply it, spray it, run the tunnel. Sometimes you get it, sometimes you do not get it. You really do not know when you will get the correct balance, and that may happen at the end of the day, and you are happy that you got the balance right. So, next day onwards you are going to get great experiments. Next morning you do not get it because the humidity has changed slightly. So, it looks very simple, but I will tell you this could end up becoming a very frustrating venture, especially at low speeds. I have tried doing many things in high speeds, but I personally feel that I could get those things easier than these, and not that they will always tell you a lot, but again there is a bit of training which you have to go through, and then you can perhaps see more when you look at an oil flow. So, there are nice papers written on flow topology. So, I have personally learned many things from such papers. So, I can give you those references, they are not mentioned immediately over here, but when you look at oil flow, those inputs can help you to identify that from an oil flow what to decipher, how to decipher, and be sure that what you are deciphering is right. Does it tell you something about the flow topology? Are there nodes, are there saddles out there? Is there a separation, is there a reattachment? How do you identify it? So, you need to understand that what is the footprint of each of those phenomena, and then you know that even oil flow, though it has been there for ages, is not something that we need to consider as a very rudimentary thing which can be dumped in this modern age. No, I certainly do not agree. So, I think with that we will end the session today. So, tomorrow morning we are going to discuss about some work on flapping wings, and we have done some preliminary measurements using particle image velocimetry. We are also doing some work using load cells, so that we can make certain force measurements on such equipments, and we found that there are several more difficulties encountered when we have a flapping kind of a configuration. So, what were the difficulties and how we tried to solve them? Few things here and there I will try to discuss on the next lecture tomorrow morning.